Okay, this first video is going to walk us through how we determine the order of a reaction from experimental data. So just as a reminder, our rate law is written as rate is equal to K, which is just a constant dependent upon whatever chemicals we're using, times the concentration, that's what we mean by the square brackets, of each chemical here, A, B, and C, raised to some power. And so the powers here are 2, 1, and 0. So the power or exponent or superscript is called the order of the reaction. And so the order with respect to A is 2, the order with respect to B is 1, and the order with respect to C is 0. Normally, if there is an order with respect to 0, we don't put it in the rate law. And that's because any number raised to the 0 power is 1. And so we just wouldn't write that. And that just means that that chemical rate does not depend on that reactant. Sometimes that might be something like oxygen in the air is just so abundant that we don't really have to worry about that. And so there's just an excessive amount of it. And so then we have what we call a pseudo rate law that wouldn't necessarily apply in different conditions. And sometimes it's just something that's not involved in the rate limiting step. We also, if we have an exponent to 1, like we do on B here, we probably wouldn't write the 1. As I say, 1s are invisible in chemistry. So, and just a reminder that you can't get this just by looking at the reaction equation. This has to be done experimentally. So one method of doing this is by comparing the initial rates and the concentrations of the chemicals. So let's see how that looks. So here we have an experiment that involves a reaction between oxygen and nitrogen monoxide. And this table includes 5 experiments. I'm just looking at 2 of them right here. And I'm going to zoom in just a little bit so that we can take a look at what's going on here. So in the middle, we have the concentrations of oxygen and of nitrogen monoxide. And we can see that oxygen's concentration changes from experiment 1 to 2, but nitrogen monoxide stays the same. And so what this is telling us is that whatever changes we observe cannot be because of nitrogen monoxide. They're probably attributable to the changes in the oxygen. So now if we look all the way over on the right-hand side, we will see the initial rate. And we look at the initial rate because remember that concentrations are going to change over time. And so as we have the reaction progress, these concentrations won't be the same and the rate will change. But right at the beginning, we do know what the concentrations are. So if we can look at the rate at the beginning, the initial rate, then that's something where we know the concentrations. So let's zoom in on this a little bit. Here we see that oxygen's concentration is doubling, and we ask ourselves, what's going on with the rate of the reaction? So we can plug in the whole number here, 3.21 times 10 to the minus 3 and 6.40 times 10 to the minus 3 into our calculators, and we would see that that's roughly doubling. Now, if you have your exponents are the same for both numbers, like the 10 to the minus 3 on both of these, we can also say that we can just plug in the 6.40 and the 3.21. I like to take the larger number and divide by the smaller number there. Okay, so our observation is we double oxygen and that doubles the initial rate. And this is going to tell us that this is a first order reaction. And we'll talk about why that is mathematically in a little bit. But basically, if the rate is doing the same thing that the concentration is doing, then we have a first order reaction. All right, what if we look at some more experiments? So here we have 5 different experiments. So we could also look at experiment 4. Let me pull up a highlighter here. Experiment 4 also has the same concentration for the nitrogen monoxide. And so we could look at that too. But what I want to do is look at how the nitrogen monoxide changes and oxygen stays the same. So we are just going to look at experiments 1, 3, and 5. And so we can see oxygen is staying the same, and we will focus our attention on the nitrogen monoxide. So let's zoom into that area again. And we can see going from the first experiment to the second, 1.3 to 2.6, that's doubling. But if we look at the initial rate, 3.2 doubled would be that 6.4 that we saw in experiment 2. And that's not what we see here. We see 12.8. So if we plug that into our calculators, we're going to find that we have quadrupled or roughly quadrupled the rate of the reaction. So this has a different order. Now, if we look at the second and the third, the third and the fifth, which are here, the second and the third experiments, then we have a change that is 1.5. So I would avoid looking at that, but you can just divide the bigger one by the smaller one to see the relationship. What I'm going to look at is the first one and the third one. So going from 1.3 times 10 to the minus 2 to 3.9 times 10 to the minus 2, that is a threefold change. So again, the nitrogen monoxide has tripled in concentration going through those experiments. The initial rate goes from 3.2 to 28.8 times 10 to the minus 3 in both cases. So this is more than doubling, but we did have 3 times as much concentration. So what would 3 times as much be? Well, that would be closer to 9 or 10. And it's even more than 6 times as much. That would be around 19. So if we plug this into our calculators, we're going to find this is a 9-fold increase. So what do we have? Nitrogen monoxide increases by 3. The rate increases by 9. Okay, so what this is saying is that going from these 2 experiments, I've doubled here and quadrupled here. And going from the first and the last experiment, I've tripled the concentration and 9-fold the initial rate. So if you remember back to some of the facts you may have learned in earlier years in math classes, the relationship between 3 and 9 is that 9 is 3 squared. The relationship between 2 and 4 is that 4 is 2 squared. So what that tells us is that squared is really important. That 2 is the order of our reaction. All right, so in summary, for first order reaction, if I double A, the rate is going to double. The rate is approximately proportional to the concentration. Whatever the concentration does, the rate does the same thing. Okay, so same is first order. For a second order, if I double the concentration, so here let me say B, that was our nitrogen monoxide, the rate is going to quadruple. And that means our relationship is the rate is proportional to B squared, or the concentration of B squared, which would mean that if I tripled it, it would be 9-fold. If I did it 5 times as much, then I would end up with 125 times the rate. So it can go up very, very quickly. But what if we have a 0 order reaction? If it is 0 order, the rate should not depend on the concentration. There's no dependence. So the rate is proportional to 1, which basically just means that whatever I do to C, it's not going to change my rate. Okay, what if I wanted to look at this more rigorously or more mathematically? I'm going to do as I did before, find the appropriate experiments, making sure only one of the reactants changes at a time, so only the oxygen or only the nitrogen monoxide. Divide the rate by the larger rate by the smaller rate, divide the larger concentration by the smaller concentration. So over here, I have the rates on the left-hand side and the concentrations on the smaller side, or on the left-hand side. I'm going to raise this left-hand side to some power n. And really, it's easiest to just kind of eyeball this. So what would make this true? What power of n makes this true? Now, we're only going to look at 0, first, and second order. So you really only have 3 things that you can try. It is possible to have higher orders like 3, to have half, or to even have negative if you have an inhibitor involved. But we'll just look at these 3 cases. And so you can really just try each of those and see which makes sense. So if this doubles, I would have a 2 on this side. And if this doubled, well, to make 2 equal to 2 to the n has to be 1. So n is the order of the reaction. If the rate triples and what goes on inside the parentheses here goes up by 9, in order to make, I'm sorry, if the rate goes up by 9, but the concentrations have only tripled, then in order to make this statement true, I would have 9 is equal to 3 to some power n, and that would be 2. The other way you can think about this is either the rate and the concentration are doing the same thing, that's a power of 1. The rate is doing a lot more, that's a power of 2, or the rate is not affected, that's a power of 0. So that's the determination of the order in a nutshell there. So let me pull up the one we did in class the other day, and we'll take a look at how that one works as well. Oh, this is a slightly different one. Okay, so here we are looking at NO2, nitrogen dioxide, and fluorine. So we want to find two reactions where one chemical stays the same and the other one changes. So if I look at the first reaction, pull up my laser pointer. In my first reaction, the fluorine stays the same. So we're not talking about fluorine here. I can kind of ignore that. The nitrogen dioxide is doubling, and the rate goes from 2 to 4. So what's going on there? So both are doubling. If they are both doubling, they're doing the same thing. And that tells us the order with respect to nitrogen dioxide is 1. All right, so take a second to look to find two reactions where the nitrogen dioxide stays the same and the fluorine changes. So if I look at the last two equations or reactions 3 and 4, the rate of the nitrogen dioxide, the concentration of a nitrogen dioxide remains the same. The concentration of the fluorine doubles, going from 0.002 to 0.004. And what happens here? We might not be able to do this in your head, so try plugging it into your calculator. And you will find that the rate has actually doubled here. So again, we doubled our concentration and we doubled our rate. So this is also an order of 1. Then the overall order is adding those up. So 1 plus 1 is 2. So we found that the rate for each reactant, both NO2 and F2, was 1, and the overall order was 2. All right, with that information, you should be able to complete the questions on the last page of your packet for Wednesday.